In this video, we're going to look at the SIR model, which is a classic set of ordinary differential equations used to model the spread of a disease in a population. We'll see in a minute why it's called SIR. But this is essentially like a toy model for the spread of a disease. It would not be appropriate to use this model alone for something like COVID-19 because the assumptions we're about to place on our model are too limiting. So let's go through the standard assumptions imposed on the SIR model. So first, we assume that we're working with a closed population. There's no immigration. Moreover, the population that we're going to look at is assumed to have a constant size. So the time frame here is usually on the order of days or months, and during this period, we assume that there are no births nor any deaths due to any other reason. We will assume that throughout the course of the disease, the population is instantaneously mixed and people are constantly in contact with each other. So even though the disease might be prevalent or rare, we'll assume that the contact between people is the same throughout. And our model will not differentiate between different age groups or social structures that might influence transmission rates. Basically, our population is like a homogeneous and closed group of people whose behavior is uniform and consistent. All right, let's look at the assumptions that we'll place on the disease. We will assume that there is a fixed infectious period, so individuals remain infectious for the same average duration of time. After that period, they stop being sick and gain immunity. Immunity is permanent, so once you've been sick, you won't be sick again. There's no reinfection. Another assumption that we'll make is that there's no latency period, so individuals become infectious immediately upon being infected. There's no delay between catching the disease and being able to transmit it to someone else. And just like we're assuming our population is simple, we're basically saying the disease is simple as well. It's not going to mutate and it has no other means of transmission. So people catch it from each other, they don't catch it from animals. Okay, so to summarize our assumptions, we have a simple closed population and a simple disease. All right, here's where the name of the model comes from. We are going to classify the individuals in this population into three categories: susceptible, infectious, and what I will call removed, but you could also call it recovered. So we have S, I, and R. So the susceptible group is the people who have not yet contracted the disease, but they are vulnerable to infection. If the disease has been newly introduced into this population, most people at the start are going to be susceptible, but as people get sick, the size of this group will only go down over time. Remember, there's no reinfection. Once a member of the susceptible group gets sick, they move into the infectious group. These are the individuals who are currently infected with the disease and who can transmit it to susceptible individuals. So the size of this group could grow or shrink over time depending on how prevalent the disease is. Individuals who are infectious eventually stop being infectious and they move into the last box, which is what I call removed. This category includes individuals who have recovered from the disease and have immunity because they can't be reinfected, or in some models, it could be those who passed away from the disease. I'll use the language removed because basically the members of this box are no longer part of the disease spread. They can't infect others and they can't be infected again. So you could think of this like an absorbing state and it will only grow over time. So our assumption that reinfection is not possible means that the members of the population can only flow from left to right, from susceptible to infectious to removed. I should say that they don't have to go to the right, meaning that you could be susceptible forever and never get infected. So you either stay in the box on the left or you flow across all the way to the right. All right, we have three groups of people and we're going to have three major parameters. For our basic disease with all the assumptions that we placed on it at the start, all of these terms are going to remain constant for the duration of the simulation. So for this first one, capital N, I called it the starting population, but really this number will not change. If we start with 1,000 members of the population, the distribution into the different boxes might change over time, but we will always sum them to 1,000. So the total number of susceptible, infectious, and removed at any point needs to add up to capital N. That will be our assumption for most of this lesson, but at the very end, I'll show you a way to recast these equations that actually removes capital N from the equation. So we'll reduce from 3 parameters to 2. Okay, so the two parameters we must have are beta and gamma. Beta is what you could think of as a transmission rate. So this is like a measure of how likely it is for the disease to spread from an infected individual to a susceptible one. So this parameter has to incorporate two aspects into it. So one is how much contact people have with each other. The more people are in contact, the more likely transmission will occur. And then it also includes transmissivity of the disease itself, so how infectious is the disease. And then our last parameter here is gamma, which you can think of like the recovery rate. So this number indicates the fraction of infectious individuals who recover each day. I have that phrased a little differently on this slide where I'm saying that it's the reciprocal of the average number of days that an individual is infectious. So here's how that works. If the infection period is 5 days, then gamma is 1 over 5. So that's kind of like saying if you bump into an infectious person, there's a 20% chance that they're on their last day of being infectious. That means that we're going to use this as the rate at which people change from being infectious to removed. Okay, I want to check your understanding with a few questions for us to think about before we move on. So the first question is, what are the units that you would associate to each of these parameters? Okay, for the parameter capital N, this is measuring how many people there are. So essentially, this is dimensionless. It's a number of people. So that's just a count of people. There's a lot going on in beta here, but number of contacts is dimensionless, and transmissivity is like a percentage. That's also dimensionless, but then we're measuring this per day. So here I'm assuming that we're measuring time in days, but basically the unit for beta is 1 over the time measurement. And then since gamma is a reciprocal of a measurement of time, we will also say that that unit is like 1 over days. Okay, let's move on to question 2. For question 2, although I said that this model is not sophisticated enough for something like COVID-19, I still wanted to kind of raise some of the vocabulary that we used during the pandemic. So suppose the population implemented social distancing, where would you see that in these parameters? And the answer is that if people were trying to be distant socially, then they would be reducing the number of contacts they had every day. That's one of the factors that goes into beta. So with social distancing, you would expect to have a lower beta value. Okay, next question. Suppose a population were to adopt mask wearing, where might that appear in these parameters? And the answer is that if everybody was wearing high quality masks, that would reduce the transmissivity of the disease. So an infected person would be less likely to pass it to a susceptible person. That's one of the factors in beta. So again, that's an aspect that would lower the value of beta. Okay, and then my final question has to do with the famous number R-nought for a disease. This is a unitless measure of how many cases an infected person will create. For example, the measles is highly contagious, and I think the R-naught value for the measles, maybe it varies at different moments in history, is about 15. What that means is if a person is infected and they're surrounded by susceptible people, so it's a vulnerable population, they would be expected to create 15 new cases of the measles. What we're measuring there is a number of people, so again, this is like a dimensionless quantity. Can you figure out how to compute the R-naught value based on the parameters written down on this slide? Here's a hint if you haven't figured it out yet. It just has to do with beta and gamma. And one more hint if you haven't figured it out is that we want this number to be dimensionless. So I'm going to need there to be no unit of time in the final number, which means these days are going to cancel out. So you're either going to do beta divided by gamma or gamma divided by beta. Okay, here's the answer. Beta is essentially how much transmission happens per day from an infectious person to a susceptible person. And then 1 over gamma is how many days an infectious person is infectious. So it's like infections per day times the number of days will give you the total number of infections that an infectious person creates. So that's the R-naught measurement. Okay, we're not going to revisit this idea, but basically it's beta divided by gamma. So while this model is a toy model, we can connect the parameters that we're looking at to this very famous way to classify infectious diseases. Now let's look closer at the mechanics of the infection process. Let's start with how the population flows from the S box to the I box. I'm going to break this computation up into pieces. So first, let's just consider the probability that on any given day, a susceptible member of the population gets infected. So that's the probability of these three concepts. For a susceptible person, we're going to take the number of contacts they make per day multiply that by the probability that a contact is infected, and then multiply that by the probability that an infected contact infects you. So that's contacts per day times the probability a contact is infected times the transmissivity. We have all that we need to translate these three ideas into a math equation. Take a moment to see if you can write down the expressions that need to go into this product. Okay, I ordered them a bit strangely here, but the product of the first and last terms is actually what's going to go into that number beta. So again, that's how socially in contact people are times how transmissive the disease is. And then the probability that a contact is infected is the number of people who are infected divided by the total population. So that's part divided by whole, it's a percentage. So that's the quotient of I divided by N, part per whole. So there are like really three things going into this, but in a nutshell, it's like the more people you come in contact with, or the more the disease is present within those contacts, or the more contagious the disease is, or any of those all together, the higher the chances are that you'll get infected. Okay, but all of that was just for an individual member of the susceptible population. To figure out how many infections should happen, we want to scale that product by the size of that population. So the number of infections for the total susceptible population on any given day should be that number multiplied by the size of that population. So that's beta times I over n times S. And then I'm just going to reorganize that in my notes as beta divided by n times I times S. That's just how I like to write that. Okay, so that's going to be our flow rate from the S box to the I box. It's a little easier to measure the flow from infectious to removed. Again, starting with the level of an individual member of the infectious box, what we want to figure out is, of all of the days that they are infectious, what's the chance that it's their last day? Because if they're on their last day of the infection, they're about to move into the removed box. But that's really how we defined that parameter gamma. What we said is that every infected person stops being infected after 1 over gamma days, which means that the chance that an infected person will flow into the removed box on any given day of their infection is just gamma. Again, because there's this reciprocal action here, let me remind you of the example that we had with that parameter. If the infectious period was 5 days, so if you were sick for 5 days, gamma was 1 over 5. That's like saying that any day that you're infected is 20% likely to be the last day of the infection. So if you just randomly find an infectious person, there's a 20% chance that that person's about to flow to the box called removed. Okay, that's the probability for a single member of the infectious box, but again, we want to scale that number up by the total number of infected people. That gives us a flow rate of gamma times I. Okay, let's put it all together. What we want to do now is convert this compartmental model into a set of ordinary differential equations. Here's how we do that. The diagram we have here shows the flow over discrete unit of time, like the daily average. But the reality of the movement between these boxes during an epidemic is that it should be continuous. So while your actual data measurements may happen in discrete steps, like you get daily updates, we're going to treat the process as continuous to get a good representation of the overall dynamics. So when you convert a compartmental model into a set of differential equations, what you say is that the flow rates here are going to turn into rates in versus rates out. So the rate of change of the susceptible population with respect to time, or dsdt, is the flow in minus the flow out. There is no flow in. So overall, that's going to be negative beta over n times I times S. On the other hand, the infectious box does have in and outflows, so overall we're going to say that it's the flow in, which is beta over n times I times S, minus gamma times I. And then the removed box only has a flow in. So dr dt will be gamma I. So this is our continuous model for how populations move from one box to the next. I have here a set of 3 equations, but we can actually make a simplification. Since our total population size n is constant, and every individual in this population has to be in one of these 3 compartments, these are not 3 independent populations. We can verify that that agrees with the equations we've written down. So if we compute the rate of change of n with respect to time, what we're going to say is that's ds dt plus di dt plus dr dt. And if you look over at the equations to the right, you'll realize that everything cancels out. In particular, we can solve for, say, the removed population in terms of N, S, and I. That's the easiest approach because if you look at the equations on the left, we have I and S, but we don't really see R in the rates of change. So instead of viewing this as a triple of differential equations, we'll view it as a pair of differential equations for ds dt and di dt. And then we'll say if you have the solutions S and I, you can write down a solution for R as well by just doing N minus the function for S minus the function for I. We're not going to find explicit solutions here. What I'm actually going to do is show you some results in MATLAB. Okay, I'm going to show you a few different models, but they're all going to be based on the same values of n and gamma. The only thing I'm going to change is the parameter beta. So suppose that we start with a population of 1,000 and say 6 come back from vacation and they're ill. What that means is on day 1, 6 people are infected, 94 people are susceptible, and no one has recovered. Our parameter gamma will be 1 over 10 because we're assuming that recovery takes 10 days. Here's what a plot of the solutions S, I, and R look like when beta is 0.4. The numbers are kind of small in this graph here, so let me tell you what's going on. On the y-axis, we have the number of individuals. That refers to each of the populations S, I, and R. And the scale on the y-axis goes from 0 to 1,000. On the x-axis, we're measuring time in terms of days. Now you can choose how long you want this model to run. I've just set it to be 100 days. So the scale on the horizontal axis goes from 0 to 100. The shape of S and R should agree with your expectations. So we start with 94 people in this population who are susceptible. We assume the population is mixing, which means that many of them become infected. So the susceptible population is a decreasing function. On the flip side, as people get infected, they move into the removed box after 10 days, so the R function grows. Those two curves should always have that basic shape. And then what we see is the infected curve grows as the disease becomes more prevalent in society, but eventually it gets fairly saturated and more people have immunity. So as the number of susceptible people drops, that infection ends up dropping as well because there aren't as many people left to infect. So that is also the typical shape for the I curve. It goes up and then it goes down. Okay, let's go through some questions to check your understanding. So my first question is, how many people were sick on day 30? I don't mean actually compute that, but rather, how would you read that from this graph? And you would find that piece of information here. So whatever the value of the I population is on day 30 reflects how many people are sick on day 30. Okay, so let's say this first month that we're tracking this disease for has 30 days. My follow-up question here is how many people were sick at any point during this first month? So how would you get this information off of this graph? Well, there are two ways that you could do it. The first is that you could look for the people who are currently sick and the people who were sick in the past. So if you add together the values on the I and R curves at day 30, that would give you the total number of people who were sick at some point during the first month. The second way to do that might be a little bit faster, and that's to look at the amount of people who weren't sick at all in the first month. That's the value on the susceptible curve at day 30, and subtract that from the total number n. So 1,000 minus whatever this value is on the S curve. Okay, for question 3, what I'm going to do is change the beta value. So I lowered beta from 0.4 to 0.3. Before we address question 3, I want you to think about what that means for this population. So what does a lower beta value reflect? Beta incorporates two aspects, how much the population mingles and how transmissive the disease is. So one of those numbers at least got lowered. Either this population is less social or maybe the disease is less contagious. Let me go back to the picture with beta equals zero point 0.4 just so you can compare how these three curves changed. Qualitatively, the curves still have the same shape. S is decreasing, R is increasing, and I peaks and then goes down. But what you might notice is that this I curve shifted. Because this transmission parameter beta is lower, it's like the disease was never quite as prevalent in society as it was when we had a higher beta value. So that peak went down. Okay, let's answer the third question. Check your understanding here. Looking at this plot, how would you get this information? How many people avoided getting sick by day 100? And that would just be the value of the susceptibles on day 100. So, how many people never got sick is how many people are still susceptible. I can't tell how low this I curve is, but if it's low enough, you might say this epidemic is over. So, this would be the number of people who never got sick during the epidemic. Okay, here's another question. Suppose 10% of infected people need hospital care and the local hospital has 20 beds total. Are there enough beds? Now, this question is a little bit tricky because we want to assume that contact mixing, like the socialization of the population, is constant. So somehow we have to imagine that the people who are hospitalized are still in contact, like maybe they're being visited. Because if I say these people who are infected are no longer mingling, then we're actually going to have to change the model. So let's just assume that this doesn't affect the contact between members of this population. Okay, see if you can answer this question based on this graph. What I would do is look at the maximum number of people who are infected at any one time. Based on the graph, that's about 300, a little over that. 10% of that is 30. 30 is greater than 20. So, what we would conclude is around the peak of this epidemic, there were not enough hospital beds. So, if you were modeling this on day one, you might want to tell this population that they need to implement social distancing. Okay, so let's say that happens. There's some sort of social distancing or other safety measures put into place, dropping the beta rate down to zero point 0.2 on the first day. Again, you'll notice the S curve decreases, the R curve increases, the I curve takes that up and down shape. But of course, there's some differences between this and the previous graphs. So, my question for you is what has happened as a result of this increased social distancing or mask wearing? And just based on how these curves shifted, I would make two main conclusions. The first is that the infected rate in the population never exceeds, say, 200. So we push down that maximum value for the I curve. In fact, if this was the same population as a minute ago, they would not run out of hospital beds. However, lowering the top of that I curve came at the cost of the duration of the epidemic. So while the vertex for the I curve came down, it also shifted right, which means it looks like at day 100, there's still a measurable amount of infected people. So this epidemic might last longer than the previous two. Maybe a third observation, though, is it looks like fewer people will ever get the disease. So while people were infected and that susceptible number came down, it didn't come down nearly as low as it did, say, when beta was zero point 0.4. So fewer people got sick. At this point, we've finished our main analysis of the SIR model, but I want to take you through an alternative formulation. What this is going to do is remove the parameter n by recasting the populations as percentages rather than numbers of people. So let me call them little s, little I, little r. And what each of these is it's the ratio part per whole relative to how we originally defined the populations. So we'll divide out the original s, I, and r by the total number n. With the examples we were just looking at, that means that on day one, little s would be 0.94, whereas little I would be 0.06 and little r would be 0. Since we're just talking in terms of percentages now, it's like you don't need to have 0 to 1,000 on your y-axis. It would go from 0 to 1, reflecting 0 to 100% of the population. Let's see what that does to the flow rates in differential equations. So first, let's take the equation little s equals big S divided by n and differentiate both sides with respect to t. When we do that, we have ds dt, where that's little s, is just ds dt, the original s, divided by n, because n is just a constant. So when we take the equation we had and divide it by n, you could write that as negative beta divided by n squared times I times s, but there's a better way to do it. And that's to individually divide both capital I and capital S by capital N, because now we have part per whole, and those are little I and little s. So looking at these new populations, we can say ds dt is negative beta times I times s. It's essentially the same thing, we just don't have that divided by n. Take a moment and do the same thing for little I. So figure out d little I dt. All right, here's what I hope you got. Just like before, it's going to be the original di dt, but divided by n. So when we set up that equation, we have 1 over n times the original right-hand side for di dt. We know what the first term is going to turn into. That's going to be beta times little I times little s. And then the second term is going to be minus gamma times I over n, but big I divided by n is just little I. So the flow from infectious to removed with this formulation is beta times little I times little s minus gamma times little I. So here would be this system of equations where R is now 1 minus little s minus I. So the removed population is also a percentage, and it's something between 0 and 1, so 0 and 100%. I'm not going to put up any pictures of this because it's going to be the same dynamics as what we just looked at. So this wouldn't really change our analysis, it's just a different formulation. I hope you enjoyed this look at the SIR model. If you're interested, there are all sorts of variations on this. For example, you could introduce vaccination into the population, or you could introduce reinfection. So there are ways to take this problem and add conditions or scenarios. We are not going to explore this further in this video, though, so thank you for your attention.